Moving on to our next lesson, we're going to look at half reactions. The next step of balancing more complex reactions is using the half reaction method. Knowing that when Leo says grr, we really start to think of reactions in terms of two halves. If one of the half reaction loses electrons, it ends up on the product side. The other has to gain electrons, so it ends up on the reactant side. In our note pack, we see that we're to fill in the word produces and requires. If one produces electrons, that really is the Leo half reaction. And you're going to see those as products. So literally on the right-hand side of our arrow, we're going to start noticing that we're making electrons. Now, electrons appear in half reactions, but they do not appear once we combine them back to create a full balanced equation. And over here, if the other requires electrons, that's our grr. In this reaction, if we require electrons and reduction is gaining electrons, that means that we need these in our reactants. We need electrons in our reactants. So after deciding which, where the oxidation half of the reaction is and where the reduction half is, whichever one is being oxidized is producing electrons. Therefore, we would show in our half reaction, we would show electrons in the products. For the other half reaction, the reduction half, it requires electrons. Again, because reduction is our grr. Reduction is gaining electrons, and to gain them, that's on our reactant side of our half reaction method. In the whole game, as we learn to balance equations, is that Leo has to equal grr ultimately when we look at an equation, other than just eyeballing it with coefficients. And we're pretty good at that. Sometimes reactions are a little more complex and we can't just spot it by looking back and forth at reactants and products. We have to follow a series of steps that help us balance equations by splitting them in half. So we're going to look at a complex reaction and begin to split it into two parts, balance each half of them, and then put them back together. So ultimately we begin by practicing writing the half reactions. Let's go to our note pack and we want to write the half reactions for the following. We have sodium plus chlorine to give us a sodium ion and a chloride ion. Now, this is a pretty basic equation. We can probably eyeball this back and forth and go, oh, I've got two chlorines on the left, so I would need two chlorides on the right. And that's might be where we stop. Right? That's just kind of us eyeballing it. So we're going to recognize what are called half reactions. The first thing I notice is that sodium is going to a sodium ion and chlorine is going to a chloride ion. So first I'm going to start off with my sodium. I'm going to write down for my half reaction that I have sodium atom, and it is turned into a sodium ion, and it has a +1 charge. So we started here. We know that as in nature, this is as it's naturally found. It's 0, and then it is turned into a +1 ion. Now this is the beginning of a half reaction, but what I notice is that it is not balanced based on charge alone. So I have a positive one on the right side and a neutral on the left. So we just need to recognize that it's not a balanced equation. What I also notice is that my chlorine started at 0 because it is a molecular form neutrally, and it now then turned into a -1 charge over on the right on my product side. So if we were to write that half reaction, I have Cl2 on my reactants, and I have Cl -1 on my product side. So in our very first steps of recognizing how to split them apart, We take the balanced or the unbalanced equation that we're given, and we recognize that one is changing charge from 0 to +1, and the other is changing charge from 0 to -1. When I think up here with the sodium going to sodium ion, the number of sodiums are the same. I have a number 1 Na and 1 Na plus, but I have to make them electrically balanced. So remember my Na up here is 0 charge and this is +1. So to have a equal balanced side, I need to see that on my right side I need to add 1 electron. Therefore, 1 negative and 1 positive equals 0. So both sides now have the same charge. Going from Na with a 0 charge to Na plus, it has lost 1 electron. So again, we know that if I'm losing an electron back here, if I'm losing an electron, my oxidation, right? Oxidation is losing an electron. That means it is producing electrons. So here I started at 0. I lost 1 electron to form Na+. So on my product side, I have 1 electron. So this is my oxidation half reaction. Remember, Leo the lion. Oxidation half reaction is losing an electron. Therefore, my electron is on my product side of this half reaction. Now, if I look down to my chlorine, Cl2, turning into chloride ion, I can simply look and see that I have 2 chlorine atoms on the left, so I need 2 chloride atoms on the right, just to simply balance the number of atoms. Now over on the right side, we can see that my net charge is -2. I have 2 chloride ions. Each chloride is a -1 charge. So therefore I need, on the left side, on my reactant side, I need to have the same charge. Right now it's at 0. So to do that, again, we know that this top, my sodium, is my oxidation. We know that my chlorine, going from 0 to -1, is being reduced. That's my GR. It's being reduced. That means that I have gained electrons. So on the left side, so I need to add 2 electrons to the left-hand side. Now I have a -2 charge on the left and a -2 charge on the right. Again, I don't need to have my oxidation and my reduction having the same charge. I just need the left and right side to be the same for itself. So here I can have -2 on the left and -2 on the right. And up here I can have 0 on the right and 0 on the left. That's okay. And again, I'm able to look at my first half reaction. We can see that it lost electrons, with my electrons being on my product side, and my other half reaction gained electrons. My electrons were on my reactant side. Because wherever there is a Leo, there's got to be a GR. Now, taking this one step further, the game now says that Leo, the loss of electrons, has to be the same as the gain of electrons. Because if we notice, in the first half reaction, I lost 1, but in the second half reaction, I gained 2. We have to make them the same by distributing to make them equal. So in the first half reaction, we need to go back and we need to distribute everything here by 2, simply because I need my electrons lost to be equal to the electrons gained in both reactions. So I could rewrite this half reaction by distributing that 2, and I would write it as 2Na forming 2Na plus and 2 electrons given off. And again, that is simply because electrons lost need to equal electrons gained. And in this case, in my electrons lost, this was 1, and my other one was 2. So I can just simply multiply everything in my first half reaction by 2 to get those numbers to equal. And now we're going to go and add them back together, similar to Hess's law. When we looked at Hess's law, we were able to cancel out things that were the same on both sides of my arrow. So I'm going to take my arrow here and I'm going to just put it right on down. And guaranteed you better have on the right hand side again. So I rewrote that Na after distributing that times 2. So I better have 2 electrons on the right and 2 electrons on the left. So those will cancel out when I write my complete equation down at the bottom. So then I'm going to look and go, okay, I've got 2 NAs that are going to drop down plus Cl2. That will just drop down. And on the right, I'm going to have 2 Na plus and 2 Cl minus. The last thing we're going to do, because it's just smart business, is you double check just to eyeball, does it indeed balance? So I've got my 2 NAs on the left and I have 2 NAs on the right. I have 2 chlorines on the left and 2 chlorines on the right. But here's the more important part. Are they electrically the same charge on both sides? So remember, my Na was 0 and my Cl was 0. So I have 0, 2 zeros is still 0, and 0. 0 is overall charge on the left. I have 2 pluses, so this is a plus 2. And I have 2 minus 1s, which is 2 minuses. So 2 minus and 2 plus, yes. I've got my overall net is 0 on the right, overall net is 0 on the left. So what we've just done, a very beginning simple model of a half reaction method. We took an equation that I'm confident you could have just eyeballed and counted to double these, but you might have gotten a little tripped up on the NAs because looking at this, Na and Na was 1 and 1, and you could have definitely looked at this and said, oh, I need 2 chloride ions on the right. But we split them into 2 half reactions. We balanced them based on Leo and Ger to combine them back together, and then we can check to make sure that we had the same number of atoms and that they were electrically balanced as well. The charge on the left equals the charge on the right. Now in this next example, I know we already found the oxidation numbers, but I'm just going to do this real quick. Change color here, -2. So that would be -6. So this needs to be a +4. +4 and -6 would give me -2. Hydrogen's a +1. That would be -8. So this has got to be +7 to give us a -1 charge. -2. So that would be -8. So +6. +1 minus 2, and a +2. All right, so let's look at our matches here, looking for our 2 halves. One's being oxidized, one's being reduced. So we're going to look at this because you can see that my sulfur is going from a +4 to a +6. So this is going to be 1 half going SO3 minus 2 to SO4 minus 2. And we can see that my other change here is going from Mn with a +7 to Mn with a +2. So my second half reaction would be MnO4 minus 2 Mn +2. One of them will be a Leo and the other one will be a Ger. What I'm noticing, however, is there's a hydrogen and there's a water molecule. And I didn't write about them in the 2 half reactions. We're going to learn very soon when we flip the page that these are tools to help me balance. Never include them in the initial half reaction. That H positive on the left-hand side, the acid ion, it's just a proton in there, a hydrogen ion. It's used to balance the H's in a half reaction. that water molecule is a tool that we're going to use to balance oxygens in a half reaction. So if I'm looking at the first half reaction, all I'm doing in this initial step is recognizing how to break a complex reaction that I really would have a difficult time trying to eyeball back and forth to balance. Just breaking it apart into two halves, creating a half reaction. Now, the steps that we're going to use to balance these half reactions is that 8-step process that we're going to become familiar with. That's right below here. The reason I just selected this example is to make a note, note to ourselves that when I'm writing half reactions, hook together elements that aren't H's or O's. Those hydrogens and waters are now just considered tools to help me balance. It makes sense because you know the title of our chapter is actually called Aqueous Reactions. Water plays a role in every equation that aqueous reactions are involved in. With water reactions, water is a tool to help us balance. In water molecules, we have hydrogen ions. For acidic solutions, we have hydroxide ions for basic solutions. They're simply tools that we'll see to help us balance. So let's take a look at those rules. So moving on, in aqueous solutions, the key is the number of electrons produced must be the same as those required. So in other words, we need to make sure that Leo equals Ger when it comes to losing and gaining electrons. When we look back to this example, initially when I had one sodium and one sodium ion and we had one electron also produced, that was our Leo, but it did not equal our Ger, our two gained electrons, to equal that 2 minus on the right. We needed 2 minus on the left. Because those did not equal one another, I needed to make Leo. I needed to make this and multiply everything times 2. So the key is Leo needs to equal Ger. Now here is the procedure, and we're going to see that there's two different types of solutions. We've got aqueous solutions that occur in acids and aqueous solutions that occur in bases. So first I want you to, before we look at this example, I want you to take a minute and I want you to look through these 8 rules. Then we're going to go through some examples. Here's an example to write down in your note. It will be helpful when looking at these 8 rules. So we're going to use the 8 steps to balance this equation. I have MnO4 with a minus charge, so I already looked at oxidation numbers for oxygen and manganese, plus iron, a +2 ion, combined to create manganese +2 and iron 3+. Now we can look at this and we can see that I have 2 sets of pairs here. So my 2 reactions, if I'm going to write down, I can see that I have Fe going from +2 to +3, so it's lost an electron. That's my Leo. And I can see that I went from a +7 to a +2. I've been reduced. So I could write down my 2 half reactions. I've got my MnO4 going to Mn +2. And I have my Fe +2 going to Fe +3. So I've done step 1, write separate half reactions. Now step 2, for each half reaction, balance all reactants except H and O. I've got one manganese. Okay, so now we've done everything except for H and O. Number 3, we're going to balance O using H2O. So I have 4 O's on the left. I need 4 H2O's on the right. That would give me 4 O's on the right and 4 O's on the left. Now I need to, direction number 4, balance my H's using H+. On the right, I have 8 H's, 4 H2's, that's 8. So on the left, I need to add 8 H pluses. That balances my H's. On to rule number 5, I need to balance charge using electrons. Well, let's look and see what we've got so far. On the right, if I look at my charge, I have a charge of +2, right? I have 1 manganese +2. My 4 waters don't have a charge. It's neutral. On the left, I have 8 H pluses and 1 permanganate, which is a minus. So I have a total of 7 plus, or +7. So in order to balance my charges here, on the left, I need to add 5 electrons. 5 electrons plus my +7 is equal to +2. So on my top half reaction, I have now balanced my charges. Now, if you notice for my half reaction number 2, I don't have to go through step, well, I have 1 iron and 1 iron, so I already wrote my second half reaction. It's already balanced. I don't have any O's or H's, so I don't even have to do step 3 or 4. But that does bring me up to 5. I need to balance my charge using electrons. So my more positive side is my right side, my product side, where I have 3 plus. So I need to add an electron to get it down to my right side being +2 and my left side being +2. Now looking at rule number 6, it says multiply equations to make electrons equal. Now remember, Leo needs to equal Ger. And if I look up here on my first half reaction, I gained 5 electrons. And on my second half reaction, I lost 1 electron. So I need to multiply everything in my second half reaction by 5. It needs to distribute so that my lost is equal to gained. So that's going to distribute and give me 5 Fe2 pluses, 5 Fe3 pluses, and 5 electrons produced. That will satisfy number 6. We can also then go back and we can label these. We didn't label which one was oxidizing and which one was reducing. We could say, since we can see we have 5 electrons on the left, it's gaining 5 electrons. This is definitely my Ger. Gaining this is my reduction half reaction. And since I have 5 electrons on my right, that means it's losing. That's my Leo. That's my oxidation side. Now let's combine. Let's see what my net reaction is here. So we can see that we can cross off my 5 on my left and 5 on my right. It's going to cancel out. And I'm dropping down my 8 H pluses plus my MnO4 minus plus my 5 Fe plus 2s, and that's going to combine to create Mn plus 2 plus 4 waters plus 5 Fe3 plus. Now let's make sure that our everything is equal. I've got 1 manganese on the left and 1 on the right. I have 5 irons on the left and 5 irons on the right. I have 8 H's, and 4 O's and 4 O's. Now let's check for charge. I've got 8 positive plus a -1, so +8 minus 1, and 5 plus 2's, so that would be +10. So that's 18, 17 plus 17 is my total on the left. Now let's look at my right. I've got 5 3 pluses, so that's +15. This is neutral, and a +2. So 15 plus 2 is +17. So my charge on both sides equals the same. Let's look at this half reaction that's in your notes, letter A. I have hydroxide on the left, and I have molecular oxygen on the right. So let's look at first thing. This is one of the separate half reactions. Well, for each half reaction, let's balance all reactants except H and O. Well, they're both just H and O, so we're going to skip number 2. Now we're going to balance our O using H2O. So on the right, we can see I have 2 oxygens. So on the left, I need 2 oxygens. And so in order to balance that oxygen, I need to add an H2O on the left. All right, so now I have 2 O's on the left and 2 O's on the right. So I can move on to direction number 4, where it says balance the H using H pluses. Well, on the left, I have 1, 2, 3 H's. So on the right, I need to add 3 H pluses. All right, now let's look at my overall charge. If I look at my charge on the left, it is -1. If I look at my charge on the right, it's +3. So the charge to the more positive side, I need to add electrons. And in order to get to a -1, I need to add 4 electrons to the right. Now, if I look at my overall charge, and I'm going to delete that here. Now I can look at my overall charge. 4 electrons and 3 protons gives me an overall net -1, so both sides are equal. Now, if this were an acidic solution, we know that we would be done. But this is a basic solution, which means we have to turn the number of protons on the right-hand side that we added, and we need to neutralize those by adding the base ion to create neutral water. So since I have 3 protons on the right-hand side, I'm going to create 3 hydroxides. And if I do that on the right, I have to do it on the left. So now, on the right-hand side, my 3 protons and 3 hydroxides form 3 water molecules. Now that's simplified over here. And on the left, if I have 3 water molecules on the right and 1 water molecule on the left, I can eliminate 1 on the right to make that 2 and cross that off on the left. I can also simplify, and if I have 3 OHs plus 1 OH, that gives me 4 OHs on the left, 1 molecular oxygen, 2 waters, and 4 electrons. Now let's check and make sure that everything is balanced by atoms and by charge. So I have on the left-hand side -4 charge, 4 hydroxides. Each hydroxide is a -1 charge. And I have 4 electrons, and both of these are neutral. So -4 and -4. We're good there. I have 4 O's on the left, and I have 1, 2, 3, 4 O's on the right. And I have 4 H's on the left and 4 H's on the left. There we go. What we've done here is that we have balanced our redox reaction in a basic solution by adding hydroxides in the same quantity as the remaining protons after we've balanced the half reaction. Now, keep in mind that this is not a complete reaction. It's just a half of a reaction. So there was a complete reaction, we separated it. This is 1/2 of a complete reaction. So just a note, this has already been broken in half. We would also, looking at just this half, we could be able to tell that this is, this is a Leo or a Gur. We can tell that because my electrons are on the right-hand side, that means it's losing electrons. So this would be an oxidation half of the reaction. Another half reaction where I have titanium dioxide and, as a reactant, and we have titanium 2 plus as a product. So I'm going to go through my rules here. Number 1, we wrote the reaction. Number 2, for each half reaction, we're going to balance the reactants except H and O. And I can see here that I've got 1 titanium and 1 titanium, and we are not balancing the O's yet. Well, let's go on to number 3. Let's balance our O using H2O. Well, on the left, I have 2 O's. So on the right, I need 2 H2O's. That gives me 2 oxygens on the right. All right. On the left, now we need to balance our H's. We now have 4 H's here on the right. So I need 4 H pluses on the left. All right, now let's look at what our overall charge is so we can balance our charge using electrons, which is step number 5. So I'm going to look at my left side and I'm going to say, okay, I've got 4 plus on the left because of those 4 H pluses, because our titanium dioxide is neutral. On the right, I have my 2 waters, that's neutral, and I have 1 titanium 2 plus, so just plus 2 on the right. So the side that is more positive needs electrons. So we need to add 2 electrons on the left to make that plus 4 go down to a plus 2 so that both match. Now they are the same electrically balanced charge. And let's see what type of reaction this is. We have our electrons as part of gaining electrons because it's part of my reactants. So this must be a reduction half reaction. Reduction is gaining electrons, and we're gaining because we can see our electrons are on our reactant side. Let's do another practice. The next one, here we have ClO3 as a reactant, and my product is Cl minus. So first thing we need to do is, this is our half reaction here. So let's balance our half reaction. I've got 1 chlorine on the left and 1 chlorine on the right. Now let's balance our O's. I have 3 O's on the left. So that means on my right, I need 3 waters to give me 3 O's on the right side. But now I need to balance my H's using H plus. So on the right side, I have 6 H's. So on the left, I need 6 H pluses. Now I need to look at what my charge is. So I'm going to, on the left, I've got 6 H pluses and 1 ClO3 minus. So on the left, I have plus 5 as my overall charge. And on the right, we can know that my 3 waters are neutral and I have 1 chloride ion, so it's a minus 1. So that also tells me that I need to add electrons to my more positive side, which is my reactant side. I need this to get down to -1. So I need to add 6 electrons on the left side. If I add 6 electrons to my reactants, then I will have a -1 charge on the left, which is equal to a -1 charge on the right. Therefore, if I wrote my net equation now, I would have 6 H pluses, and again, this is just for my half reaction, plus 6 electrons, plus ClO3 minus, and on my product side, I would have Cl minus plus 3 H2Os. Again, I can tell that because I have my electrons gaining electrons, it's on my reactant side, that this is a reduction half-life reaction. Let's look at this next example under our basic solutions. Again, we're going to do everything we would with an acid, but there's one more step. We're going to add enough hydroxides to both sides to neutralize the H+. So we have sulfite converting into sulfate. So we have SO3 2 minus going to SO4 2 minus. So we're going to go through the 8 steps just like we've done with the other problems. Number 1, this is our half reaction. So I can say I've got one S and one S on both sides. All right. Number 2, we're going to balance. Oh, that is number 2. Number 3, we're going to balance our oxygens. So I have 3 oxygens on the left. I have 4 oxygens on the right. So I need one more oxygen on the left. So let's add an H2O. That gives me another O. So I have 4 O's on the left and 4 O's on the right. The next thing I need to do, number 4, I need to balance my H's. Because I added that water, I added 2 H's on the left. So I need to add 2 H pluses on the right. That balanced my H's. Now let's look at our charge. I'm going to look at this. I have one SO3 with a -2 charge, so I have -2 on the left. And if I look over here, I've got a -2 and 2 +1s. So I have a neutral charge on the right. The one that is more positive needs electrons. So the one that is more positive would be my product side. I need to add 2 electrons to the right side to give it not just a 0 charge, I need it to be a -2 so that these equal. Therefore, this is telling me since I have electrons on the right-hand side, this is a Leo. We have lost electrons. This is an oxidation half reaction. Now, if this was an acid, if this was an acidic solution, we'd be done. But we're told up here that it's a basic solution. And basic solution tells me that I need to add hydroxides to cancel out these H pluses. So I've got 2 H pluses on the right. That means I need to add 2 OH minuses to neutralize those H pluses, which is going to combine to form 2 waters. Because I added those 2 hydroxides on the right, I need to add 2 hydroxides on the left. Now this is kind of becoming messy, so let's see what we have here. I've got on the left-hand side, I'm going to bring my arrow down. I've got a water, I've got 2 hydroxides, and I have my sulfite, SO3, 2 minus. On the right side, I have sulfate, SO4, 2 minus. I have 2 waters, and I have 2 electrons. Well, we can do one more simplifying here. I can look and see that I've got a water on the left, and I have 2 waters on the right. So we can just subtract 1 water, get rid of that, and this 2 waters goes down to 1 water. So 2 minus 1 gives me 1. So here's my half reaction. I have 2 hydroxides plus a sulfite. And I can also verify that I have a total net 2 minus and 2 minus. So I have 4 minus on the left. And on the right side, I've got an SO4 2 minus and 2 electrons. That's also a -4 on the right. SO4, 1 water, and 2 electrons. This is a balanced half reaction for a basic solution. Let's do some practice here, identifying the oxidizing agent and the reducing agent in these redox reactions. Remember that the oxidizing agent is the one that's being reduced. And the reducing agent is the one that is being oxidized. So let's look and see which one is which. I have nickel plus chlorine to give me nickel chloride. So this is a combination reaction. Again, we know that combination is a redox reaction. Nickel and chlorine, we both know as in their elemental form and molecular form found in nature are 0. And then we can look at our compound here to figure out its oxidation numbers. Chlorine is a -1, which gives, with 2 chlorines, that's a -2, so nickel must be +2. So my nickel went from 0 to +2. So therefore it was oxidized, right? Leo the lion says grr. If it was oxidized, it lost electrons. It loses electrons, so it becomes more positive. If it was oxidized, that means that nickel is the reducing agent. Remember, we're looking at the reactants when we're identifying agents. So nickel went from a 0 to a +2. It was oxidized. Nickel is the reducing agent. Chlorine went from 0 to -1. It gained electrons to go from 0 to -1. So it is it's going through reduction. It's going through reduction. That means it is the oxidizing agent. So Cl2 is the oxidizing agent. Let's look at this next one. It looks like a single replacement reaction. I've got iron nitrate plus aluminum to give me iron and aluminum nitrate. So let's look at our oxidation numbers here. We can look at our iron, and this is not a balanced reaction here. We would have 3, 3, 2, 3, 2. That looks right. My Fe is a +2. My aluminum in natural form is 0. Fe is 0, and here we have aluminum as a +3. So we can see that my iron went from +2 to 0. So because it went from +2 to 0, it was reduced. That means that it gained electrons. If it was reduced, that means it's the oxidizing agent. And that reactant, this iron that was reduced, the reactant is FeNO3 2 is the oxidizing agent. Looking at aluminum went from 0 to +3. So therefore it lost electrons. That is the Leo. So the aluminum was oxidized. So the reducing agent is just aluminum. Remember, we're looking at just the reactant. Yes, the iron was oxidized, but the whole reactant is the iron nitrate. Number 3 looks like it's another single replacement reaction. Let's look at our charges here. I've got magnesium 0. Pb is a +2. This is a -1. This is a +2, -1, and this is 0. So my magnesium went from 0 to +2. So it lost electrons. That was it was oxidized. Therefore, it's the reducing agent. My Pb went from a +2 to a 0. So it gained electrons. The lead went through reduction. That means the lead chloride is the oxidizing agent. PbCl2, the oxidizing agent. And then number 4 looks like another single replacement. And I've got nickel by itself is 0. My HNO3, so we've got H is always +1. This is -2, so that's -6. -5, so this has got to be +5. Then my nickel here, +2. My nitrogen over on the right side would be +4, because that's a -2. So my nickel is going from 0 to +2. Therefore, it has lost electrons. It was oxidized. Therefore, it's the reducing agent as my nickel. And so if my HNO3, if I look at my N went from +5 to +4. My nitrogen was reduced. Therefore, my oxidizing agent is my whole reactant here, my HNO3. It's my oxidizing agent. Moving on to the next part of the notes, where we're going to balance redox reactions by the half reaction method. I'm given MnO4 and CH3OH, and it's producing HCO2H, and this is a key part that was accidentally left off of your notes. Make sure and add manganese with a 2+ charge. So I added in the oxidation numbers above them. And again, same review from the very first lesson. We know oxygen's always a -2. And so there's 4 oxygens, that would be -8. My whole polyatomic ion is -1, so manganese must be +7. Now I'm going to find manganese's pair on the other side of our reaction over here on the right, and it's a +2. So going from +7 to +2, that means that it has gained electrons. So this is my reduction. Manganese is being reduced. Therefore, it's the oxidizing agent. Okay, but it's not asking us that. But let's write our half reaction. So we know that MnO4, and it's going to Mn2+. So before I even write the LEO, because this is our GER, this is our reduction half, let's balance it. So we're going to go through our steps. I've got 1 manganese, 1 manganese. We're good. Next, I need to balance my oxygens. I have 4 oxygens on the left, so that means I'm going to need to add 4 waters on the right. Now I have 8 hydrogens on the right, so I need 8 H pluses on the left to balance out my hydrogens. Next, I need to look at charge. Okay, so if I look at, here we go, charge, I've got 8 pluses and 1 minus, so I have a +7 on the left, and on my right, I just have +2. Now we need to add electrons. So who needs to become more negative? Well, my left side, I need to go from +7, I need to add 5 electrons to make that +7 go down to, so +7 and 5 electrons, that now gives me a +2 charge. Okay, so my first half reaction is set. Now let's look at my next one. We need to figure out my oxidation part. So if I look at my other reactant, what's being oxidized? Well, it's not my hydrogen because I have +1 and +1 on the left and the right side. Hydrogen's the same. Oxygen is the same, -2, -2. It's the carbon. Notice that my carbon went from -2 to +2. It's being oxidized. So we have my CH3OH on the left, and on the right I have HCO2H. Okay, let's balance my carbon. 1 carbon, 1 carbon. We're good there. Now let's balance my oxygens. I have 1 oxygen on the left and I have 2 oxygens on the right. So I need to add an H2O on the left. That now gives me 1 O and 1 O. That's 2 O's to equal the O's on the right. Okay, now we need to balance H's. How many H's do I have on the left? I've got 1 plus 3 is 4, plus that 2 is 6. I have 6 H's. I need 6 H's on the right. Right now I only have 1, 2. So I need to add 4 H pluses. Now let's look at our overall charge. I'll change my color to match the one from up above. I have no net charge on the left, right? My water is neutral and my CH3OH is neutral. On the right side, I have +4. Okay, I need both of these to be equal to one another. So let's take my more positive side and we're going to add electrons. I've got +4, so I need to add 4 electrons to the right. That will cross that off and that will make both sides 0. Now remember, when we combine both of my half reactions, remember that part that said My LEO needs to equal my GER as far as electrons. And we can see on the left side, in my reduction, I have 5 electrons. On the right side, I have 4 electrons. I need these to be equal, the left and the right side. So how do I get them to be equal? Well, the first multiple that they have in common would be to get to 20. So I need to multiply everything in my top half reaction by 4. And I need to multiply everything in my second half reaction by 5. Okay, so let's do some math here. Again, everything in my top is going to be multiplied by 4. So let's do that and then bring everything down here, and then we can do some reducing. So our 5 electrons, 5 times 4 would be 20 electrons. Plus my 8 hydrogens times 4, 32. 1 MnO4 times 4 be 4 MnO4s. Plus, now we've got my second one. I've got 1 water on the left, but remember we're timesing it by 5. So 5 waters plus, I had 1 CH3OH, I'm timesing it by 5. 5 CH3OH. Now let's look at the right side. I'm going to do this top part first. We have 1 Mn, but again, remember we multiplied it by 4. So 4 Mn 2 pluses, plus we had 4 waters. We had to times it by 4, 16 waters, plus we had 1, but we had to times it by 5, so 5 HCO2H, plus we had 4 H pluses times 5, so that would be 20 H pluses. And then, not finally, because I forgot about the electrons here, plus 4 electrons times 5 is 20 electrons. Now let's do some simplifying. I'm going to draw another line underneath it here. And we can look and we can see that 20 electrons on the right and 20 electrons on the left will cancel out. We can also see some similarities here. On the left, I have H pluses, and on the right, I have H pluses. On the right, I have 20. On the left, I have 32. So we can just subtract the 20 from both sides. So 20 minus 20 will cancel out those H's. And 32 minus 20 will take that 32 down to 12 H pluses. I can also see some commonality here. I've got water on the left and water on the right. I've got 16 on the right and 5 on the left. So let's just totally get rid of the 5 on the left, and we're just going to do 16 minus 5. So that would be a net of 11 waters on the right. And I think that's it as far as canceling. So now we can write our total net redox reaction. H pluses plus 4 MnO4 minus plus 5 CH3OH to give us 4 Mn2 plus 11 H2Os plus 5 HCO2H. Notice that our net final equation does not have any electrons in it. In example number 2, I'm not even going to write the oxidation number. What I'm going to do is I'm just going to find our pairs. And I'm going to look at my reactant here that has arsenic in it. And I'm going to find the product that also has arsenic in it, which I just overshot it. Arsenic, arsenic. So this is going to be one pair. And my nitrogen and nitrogen. This will be my other half reaction. And as we get into balancing it, we'll be able to figure out which one is being oxidized and which one is being reduced simply by doing all of its balancing. So I'm going to start off by writing our AS2O3 And on the right side will be our H3AsO4. And then on the other one, we're going to write down our NO3 minus 1 and N2O3. So first I'm going to start off by looking at my first reaction and balancing. Now notice on the left I have 2 arsenic, so on the right I'm going to need 2 of this compound, H3AsO4. So I balanced my arsenics. Remember, we're not balancing O's and H's yet. When we do O's, we have to add waters. When we do H's, we add H pluses. So I balanced my As. Next, let's look at how many oxygens I have on both sides. I have 3 on the left, and I have 2 times 4. I have 8 on the right. So that means I need 5 waters. Let's double check that math. If I have 5 O's plus 3 O's, that's 8 O's. And 4 times 2 is 8 O's. So I have 8 O's on both sides of the equation. Now I need to balance my hydrogens. On the left, I have 5 times 2. I have 10 hydrogens on the left. On the right, I have 3 times 2. I have 6 hydrogens. So I need 4 more H pluses. Now let's look at my overall charge. And to do that, on the left, 5 waters, so that's neutral. As2O3, neutral. I have a total net of 0. Let's look at the right side. I have a total net of 0 on H3AsO4, but then I have 4 H pluses, so I have plus 4 on the right. So that means I need to get my right side, my more positive, I need to add 4 electrons. That will get my plus 4 down to 0. Now both sides match. I could also then look at this and I can say, I've got my electrons in my product. That means I've lost electrons. This is my Leo. So I can say, my arsenic, my As, has been oxidized. Whereas the As2O3 is my reducing agent. All right, let's look at the next one, my NO3 minus to N2O3. Let's balance my N's first. Notice I have 2 N's on the right, so I need 2 N's on the left. All right. Next, I'm going to balance my O's. So I have 3 times 2, I have 6 O's on the left, only 3 O's on the right, so I need 3 waters on the right. Now let's figure out how many H's I have. I've got 6 H's on the right, so I need 6 H pluses on the left. Let's look at our net charge. On the left, I've got 6 pluses and 2 negative ones, so that's negative 2, so a total of plus 4. And on the right, I've got 0. So I got to get this plus 4. I need to add 4 electrons to get that plus 4 down to 0. It's my more positive side, so I need to add electrons. And look, I had to gain electrons. So this is my I had to gain electrons. So my NO3 is being reduced. My nitrogen's being reduced. So NO3 is my oxidizing agent. Let's do our combining here. Notice that on the right side, I love it when this happens. I have 4 electrons on the right and I have 4 electrons on the left. So we don't have to do that distribution of coefficients because we can just go, hey, look, the 4 and the 4 cancel out. So we can just bring down everything. All right, so I'm just going to bring down my 5 waters, my As2O3, my 6 H pluses, and 2 NO3 minuses. And on the right side, I'm going to bring down 2 H3ASO4s, 4 H pluses, N2O3, and 3 waters. Is there anything we can cancel out? Yes. Let's see, I've got 4 H pluses and 6 H pluses. So we can just cancel out the right side, that 4, and do 6 minus 4 to give me 2 H pluses. Anything else can we cancel? Sure. I've got 3 waters on the right and 5 waters on the left. So let's get rid of those 3 waters and make that 5 go down to 2 waters. There is my net equation here. I've got 2 waters plus As2O3 plus 2 H pluses plus 2 nitrates. Those are my reactants, products, 2 H3ASO4s and N2O3. Last example for this lecture, where we've got H2O2 plus Cl2O7. Those are our reactants. Our products is ClO2 minus 1 and O2, and it's in a basic solution. So I'm going to find my first pair here. I've got chlorine paired with chlorine, and my second pair must be this. All right. So I'm going to write down my H2O2, hydrogen peroxide, to O2. It's my first. And my second pair is going to be Cl2O7 to ClO2 minus 1. All right. First thing I'm going to do for the first one, well, we've got H's and O's. So we can start right off with, my O's are balanced. Okay. I have 2 H's on the left, so I need 2 H's, 2 H pluses, 2 H pluses on the right. Let's look at our overall charge. I have, let's change this, 2 plus on the right, nothing on the left, just 0. So that means I need to add 2 electrons on the right. Okay, top is good. Let's look at the second one. Let's balance, and by doing that, the first thing I notice is, here we go, that I've got 2 chlorines on the left, so I need 2 chlorines on the right. And let's see, let's balance our oxygens next. I've got 7 oxygens on the left and 4 on the right. So I need 3 waters, right? That gives me 4 O's plus 3 O's is 7 O's on the right and 7 O's on the left. Let's balance our H's now. I've got 6 H's on the right, so I need 6 H's, H pluses. On the left. Let's look at our total charge now. And that gives me 6 plus on the left. Let's look at my total charge on the right side. I've got 2 negative 1s, so negative 2. That's telling me my one with more positive, I need to add electrons to this side. So I need to add 6, 7, 8 electrons to get that down to negative 2 so they equal. All right. Now, to make my combined reaction here, remember my electrons need to equal one another. Here I've got 8, here I've got 2. Again, I could also look at this before I do that. I can figure out which one's my Leo, which one's being oxidized, and which one's my Ger, which one's being reduced. We can see that I'm losing electrons here. So this is my Leo, and I'm gaining on the left as part of my reactants. So this is my reduction. Not that it did not ask that, but anyways. All right, so I've got 8, I've got 2. I need them to be the same. So that means I need to multiply everything in this top equation by 4. All right, that'll cancel out my electrons here. So let's see where that gets us. So everything on the left side of my arrows, I'm going to have 4 H2O2s. plus, that's the only thing on my left for that top one. On the left, I'm going to have, I'm canceling out my electron, I'll just write them. 8 electrons, 6 H pluses, and Cl2O7. On the right side, I'm going to again multiply everything up here by 4. So that'll give me 4 O2s plus 4 times 2 is 8 H pluses plus 4 times 2 is 8 electrons plus 2 ClO2 minus 1 plus 3 H2Os. All right, let's see what we can get rid of. We can look at our 8 electrons and 8 electrons and cross those off. We can look at my 6 H's and 8 H's. I can reduce this, get rid of 6 entirely, and that 8 would go down to 2. What else do we have? I think that's it. Okay. Now, if this was an acidic solution, I could just write everything down that I crossed off or minimized. But remember, this is a basic solution. So wherever I have H pluses, I need to add that many hydroxides. So I have 2 H pluses remaining after I cancel these off. So I need to add 2 OH minuses. Remember, these will combine, and I have to do the same thing over here, plus 2 OH minuses. These are going to combine to form 2 waters. And I already had 3 waters. So these are going to combine down here to form 5 waters. So now let's write everything that we've got. 4 O2s plus 2 ClO2 minuses plus 5 waters. And on the left, I have 4 H2O2 plus 2 OH minuses plus Cl2O7. Let's double check that everything matches up. I've got 4 times 2 is 8, 9, 10 H's on the left, and I've got 10 H's on the right. Let's see how many O's we have. 8 O's plus 2 O's is 10, plus 7 is 17 O's on the left. On the right I have 8 plus 4 is 12, plus 5 is 17. And I think my last thing is chlorines. 2 chlorines on the left and 2 chlorines on the right. Now let's check charge. Charge, I have 2 OH minuses, so that's a -2 charge. And on the right, I have 2 ClO2 minuses, so that's a -2. This should be our final net equation.